In our previous lesson, we spent a good deal of time talking about the fundamental aspects of graphing two-dimensional objects in the coordinate plane. I'd like to continue to think along these lines, this sort of visual side of the fundamentals of mathematics, and look at some basics of two-dimensional geometry in this lesson. In the process, I also want to talk about how geometry is related to arithmetic. Of course, arithmetic is the overarching theme of this course, and I want to do so by talking about things like the perimeter and the area of various geometric figures. Now, the study of geometry is easily 2,000 years old, and it's really hard to pinpoint where it all began. But many historians would argue that it was Euclid who really put geometry on the map when he wrote his books, which are called the Elements. Now, with that said, I'd like to spend a good part of this lesson talking about lots of different terms and formulas that come up in geometry. Let's start with some very general facts about things called polygons. A polygon is a closed figure in the plane whose boundary is a set of at least 3 straight lines that intersect at each vertex or sharp point of the figure. The word polygon is a very interesting one, in my opinion, from a historical perspective. It's built from 2 Greek root words, poly, which means many, and gon, which comes from a Greek word which means knee, like the knee in your leg. So the idea that a polygon is made up of many angles, like when your knee is bent, is a really cool one when you think about that word. Now, before you start wondering where in the world I'm going with all of this stuff about polygons and knees and everything else, please know that you already know lots of things about polygons, and you've seen a variety of polygons in your life. Triangles, rectangles, squares, pentagons, hexagons, and lots of other shapes that you already know are all members of the polygon family. So let's dig into some of these very familiar shapes or polygons and think about some of their characteristics. I suggest we start with some of the very basic ones that we call triangles. Now, a triangle is a polygon which is made up of exactly 3 sides. And this definition makes sense if we remember, for example, that the word tricycle has 3 wheels, and tripod for your camera has 3 legs, and a triathlete competes in 3 events at a competition: swimming, bicycling, and running. So in a similar fashion, a triangle has 3 sides. And by the way, it has exactly 3 angles, which is really where the word comes from. Now, there are some very special kinds of triangles which I would like to mention right up front as we discuss this part of the lesson. First, let's think about triangles in terms of their angles. There are some different ways we can characterize triangles based on their angles, and one of the most familiar, I think, is the idea of a right triangle. A right triangle is a triangle that contains a 90-degree angle. And that means it has an angle in it which is made of 2 perpendicular lines. Or, if you want to think of it this way, a 90-degree angle is made when a horizontal line and a vertical line intersect. Just like with the axes we talked about with the Cartesian plane in the previous lesson. Now, the leg of a right triangle, which is the one that's opposite the 90-degree angle, has a special name. It's called the hypotenuse of the right triangle. Okay, so we can have right triangles, but we can have other kinds of triangles as well, and let's talk about those briefly. A scalene triangle is a triangle where each of the 3 angles measures less than 90 degrees. Every one of the angles has to be smaller than, if you will, a right angle. So that would be a scalene triangle if you looked at one of those. Next, you can have what's called an obtuse triangle. And an obtuse triangle is a triangle where one of the angles measures more than 90 degrees. In other words, you can have a really wide angle, so to speak, inside an obtuse triangle. And by the way, you can only have one such angle that measures greater than 90 degrees in any obtuse triangle. And lastly, from this perspective of looking at triangles and characterizing them by their angles, we have the phrase equiangular triangle. And this is going to be a triangle where each of the three angles is equal in size. That's where the equi comes from at the beginning of that word. And if all three angles are of the same size, and you have one of these equiangular triangles, then each angle is going to measure exactly 60 degrees. Now, there are other ways that you can characterize triangles. Instead of looking at their angles on the inside, so to speak, you can also look at their legs, and in particular their leg lengths, when you're characterizing the triangle. So let's talk about a couple of phrases that come up when you're characterizing triangles based on their lengths of their legs. First of all, an isosceles triangle is a triangle where two of the three sides have the same length. And you can also have triangles where all three sides have the same length, and that is going to be called an equilateral triangle. So an equilateral triangle has all three side lengths equal. And by the way, if you're an equilateral triangle, then you're an equiangular triangle as well. Now, from all this vocabulary that we've just discussed, it should be clear that there are lots of differently shaped triangles. Well, I don't mean that they have lots of different numbers of legs. They all have three legs. But it turns out that you can get lots of different triangles in terms of shapes and relationships between their angles or relationships between their leg lengths. It turns out that some of these characteristics, though, various characteristics, are shared by each and every triangle that you can draw, whether it's obtuse or whether it's something that has a right angle in it or something like that. So let me discuss some characteristics that are shared by each and every triangle that are true for every triangle that you can draw. First of all, the sum of the degrees of the angles inside a triangle, no matter what triangle you draw, is always going to be 180 degrees. So when you add the three angle measures, if you will, of any triangle, no matter what kind it is, that sum has to add up to 180 degrees. That's one characteristic shared by all triangles. Secondly, the area of any triangle that you write down is equal to 1/2 times the base length of the triangle times the height, the vertical height of that triangle. So the area formula for a triangle is well known. It's 1/2 times base times height. And thirdly, you can talk about the perimeter of any triangle, and it's always just going to be the sum of the three leg lengths, no matter what they are. Now, we can use these three facts to do lots of different kinds of calculations involving triangles and arithmetic. I know this lesson has felt a lot like a geometry lesson up to this point, but we can actually mix in some arithmetic now using some of the characteristics I just mentioned. So let me show you a few examples. First, let's find the perimeter and the area of the right triangle whose leg lengths are 8, 15, and 17, respectively. Now, before we can really begin this problem, we need to make sure that we can see the triangle and what it looks like. Probably the most important thing to notice is that the longest of the three leg lengths in this problem has to represent the hypotenuse of the right triangle. Remember, the hypotenuse is the leg that's across from the right angle. So this leg of length 17 has to be the one that's across from the right angle because 17 is the largest of the three lengths. Now, if we orient the triangle then on the page so that the leg of length 15 and the leg of length 8 serve as the vertical and the horizontal legs of the right triangle, respectively, then the hypotenuse is going to be the somewhat diagonal part or the diagonal leg in the drawing of the triangle. So the triangle is going to look something like this. Now, once you've drawn that, you can now finish the two parts of this problem pretty easily. Okay, so let's walk through and find the perimeter first, followed by the area. Well, first, the perimeter is just the sum of the three leg lengths. And thankfully, I gave us the three leg lengths at the original statement of the problem. So those were 8, 15, and 17. So the perimeter here is just going to be 8 plus 15 plus 17. And now you just have to add. 8 plus 15 is 23. And so the problem can be rewritten as 23 plus 17, and 23 plus 17 equals 40. So the perimeter here is just 40. Now, what about the area? Well, the length of the base of this triangle is 8 units, and the height of the triangle is 15 units, given the way that we drew the triangle as I was talking you through it a moment ago. So from the formula I mentioned about the area, I know that the area of this triangle is 1/2 times the base times the height, which is 1/2 times the numbers 8 times 15. And if I go through the calculations, just doing them left to right as I go through the multiplication, 1/2 times 8 is going to be 4. So I'm going to have 4 times 15, and 4 times 15 equals 60. So in this problem, the area of that right triangle is equal to 60. Now, I'd like us to move on and look at a similar kind of problem, but with a different kind of triangle. So here's the example I want us to look at. Find the area of the obtuse triangle that I have pictured here. Now, there's this old saying that says a picture is worth 1,000 words. Well, in this case, that picture is exactly what I needed to know in order to be able to find the base and the height of this triangle so that I could quickly calculate the area. So let's calculate that area here. We're going to use this formula, 1/2 times base times height, and we're going to plug in the values that we had in the problem. From the picture, I know that I want to have an area of 1/2 times 20 times 14. And that means that I really just have 10 times 14, because 1/2 times 20 equals 10, and 10 times 14 is 140. So the area of this obtuse triangle that we had the picture for is exactly equal to 140 units. And I want to point something out with this example before we move to the next one. And here it is. Some students are bothered when the height of the triangle isn't actually found by looking at one of the specific legs of the triangle, just like we had to do in this example that we just completed. It's important to understand that the height does not have to be one of the legs. You just need to know the vertical height, if you will, of the triangle in order to actually use the area formula, 1/2 times base times height. So even if one of the legs isn't exactly vertical, as long as you can find the vertical height somehow, you can use this area formula with no trouble. Now, let's look at another example where we have to do just a bit of detective work. So here's the example I want us to look at. Find the area of the isosceles right triangle that you've been shown here. Okay, now from the picture, we see that the base has been given to us. It's exactly 16.2 units in length. Unfortunately, the height has not been given to us, and we need that height in order to use our area formula. So what do? Well, let's go back to the wording of the original problem just to see what it was telling us. First of all, we were told that this triangle is an isosceles right triangle. That actually tells us a couple things. First, it tells us since it's isosceles, it has to have 2 legs of equal length. And secondly, since it's a right triangle, it has a hypotenuse. And that hypotenuse is the leg that's across from the 90-degree angle. Now, let's put those two pieces of information together. We know that there's only one hypotenuse in a right triangle, because there can only be one 90-degree angle. If there was another 90-degree angle in the triangle, then the third angle would have to have 0 degrees in order for the sum of all the degrees to add up to 180. But if one of the angles is 0 degrees, then you don't really have a triangle. So that means that there cannot be another leg on this right triangle that's the same length as the hypotenuse. And since this triangle is isosceles, that means that the other two legs, the two legs that are not the hypotenuse, must have the same length in this problem, thanks to the isosceles nature of the triangle. This is pretty cool. So now I go back to my picture, and what I've just figured out is that the leg, which would give us the height of this right triangle, must have the same length as the base of the triangle. And so the height of this triangle is 16.2, just like the base of the triangle was 16.2. And that's excellent. That was the piece of information that we needed in order to complete this area formula. And so let's plug in the information. The area is equal to 1/2 times the base times the height. So it's 1/2 times 16.2 times 16.2. And now we're going to have to work through a little bit of math, but it's not a problem. We've been doing lots of arithmetic in this course already. 1/2 times 16.2 is going to be 8.1. So I have 8.1 times 16.2. And now you just do a little bit of multiplying of two decimal numbers, and you'll find that 8.1 times 16.2 equals 131.22 after you do that long multiplication. So our final answer for this area is 131.22, and we see that a number of different pieces of arithmetic came into play in order for us to simplify that answer. Now, I'd like us to do one more example with triangles here. It's a very different kind than what we've done up to this point. Here it is. I want us to find the measure of the angle that is not labeled in this triangle that you see on the screen. Okay, this example requires a little thinking as well, but once we get our heads around the problem, I don't think it's going to be difficult. We know the measures of two of the angles already. They've been given to us. One of them is a 45-degree angle, and the other one is a 75-degree angle. Now, those two angles combined, if you will, when you add up their two measures, is going to be 45 plus 75, which is 120 degrees. Now, next, what do we know about what you get when you add up all the angles of a triangle? Well, I told you that fact earlier in the lesson. We know that every triangle has a total of 180 degrees. And that means that the measure of the angle that was not labeled in our picture must be 180 minus the 120, which we got from the 45 and 75 degree angles respectively. And 180 minus 120 equals 60 degrees. And so we're done, just like that. The measure of that third angle has to be 60 degrees. Now, we've spent a good bit of time on triangles, so I'd like to move forward now with a discussion of a different family of polygons, and in this case, I want us to look at polygons with four legs. We often call this family the set of quadrilaterals. Now, I'm guessing you already know some quadrilaterals or four-legged polygons. Can you think of a few four-legged polygons that you might already know? Sure, squares would fit in this category, and rectangles. They're both examples of four-legged polygons. And in fact, squares are special cases of rectangles. But it also turns out that both squares and rectangles are special cases of another family of four-legged polygons called parallelograms. So let me try to define what all these are, and then we'll look at perimeter and area questions related to these. All right, so let's get to these. First of all, a parallelogram is a four-sided polygon which consists of two pairs of parallel line segments. That's where you sort of get that piece parallel inside of the word parallelogram. In a parallelogram, you don't have to have any special angle measures like a 90-degree angle or anything like that. You just need to have these two pairs of parallel line segments in the picture, which means, by the way, that the segments in each pair will be of the same length. So here are some examples of parallelograms. Now, the next kind of thing I want to think about is a rectangle. And a rectangle is a parallelogram, but now all four angles have to be right angles. So in some sense, a rectangle is a parallelogram that has been shifted in such a way to make all the line segments either vertical or horizontal, if you imagine setting this thing on a flat surface. Again, the leg lengths in each pair will have to be the same, but not all 4 leg lengths have to be the same. You just have to have these 2 pairs of legs which are parallel to one another, and the angles all have to be right angles. So you can get lots of different kinds of rectangles. Some very long ones which aren't very tall, others that have lengths and heights which are much closer together. Now, once we've talked about that, then there's a special type of rectangle that we should also talk about, which is the square. A square is a rectangle where all 4 leg lengths are actually the same. So we've gone from parallelograms to rectangles to squares. Now, just as with triangles, there are a few facts about parallelograms, rectangles, and squares that we should always remember. Here are a few such facts. First, the sum of the degrees of the angles inside any parallelogram or rectangle or square will always be 360 degrees. That's very important to remember. Secondly, the area of any parallelogram or rectangle or square will always be the length of the base times the vertical height. That looks very much like the area of a triangle, except it doesn't have that 1/2 in it. So the area of any parallelogram, rectangle, or square will just be base times height, okay? And thirdly, the perimeter of any of these objects is, again, just the sum of the lengths of all 4 legs in this case. Now, let's do some problems involving these quadrilaterals like the ones we did for triangles a few minutes ago. Let's look at the following example. I want us to find the perimeter and the area of a rectangle with base length 15.3 and height 8.2. Now let me suggest that you try this one yourself first to see if you can find that perimeter in that area, and then we'll meet back up to see how you did. Well, the perimeter of a rectangle is pretty straightforward. It's going to just be the base plus the base plus the height plus the height. Remember that the height of the rectangle on, let's say, the left side of it has to equal the height of the rectangle on the right side of it, because a rectangle is a parallelogram and the side lengths of the opposite legs are the same. So as you go to find the perimeter, you're basically going to use the base length twice and the height length twice, and you're just going to add up those 4 lengths. And in this case, that's going to give you 15.3 plus 15.3 plus 8.2 plus 8.2. Now, before I do the arithmetic, let me point out, some of you might be saying, wait a minute, if I do the perimeter as I go around the rectangle, I'm actually going to write down 15.3 plus 8.2 plus 15.3 plus 8.2. That's different than what you just said. But remember, in one of our previous lessons, we learned that if all you're doing is adding, then it turns out that it doesn't matter what the order is in which you add these numbers. So I can write the 4 numbers down in any order I want. As long as I add them all up, I'm good to go. So let's do this perimeter now. 15.3 plus 15.3 plus 8.2 plus 8.2 is the same as 30.6 plus 8.2 plus 8.2, which is 38.8 plus 8.2, which is exactly 47.0 units in length. Okay? So I should also point out, from what I just said about the order of operations on all these additions, that the perimeter could have also been calculated as 2 times 15.3 plus 2 times 8.2. I'd be getting the same thing if I walked through that. But if you'd like to remember the perimeter this way, as 2 times the height plus 2 times the length, or 2 times the length plus 2 times the height, then you'd be good to go. In that case, you would be writing down 2 times 15.3 plus 2 times 8.2, which is 30.6 plus 16.4, which also equals 47.0 units, the same answer we got a moment ago. Next, let's look at the area of this same rectangle. And remember, the formula for the area of a rectangle is just base times height. So in this case, I'm looking at 15.3 times 8.2. And if you just complete that multiplication, as we've done in several of our previous lessons, you'll see that the area is exactly 125.46 square units. Now, I'd like to move forward with another example using squares this time. And here's that example. Let's find the perimeter and the area of a square whose side length is 10.5 units. I'm going to suggest that you pause the video at this time, try this yourself, and see how you do. Well, since a square is a very special kind of rectangle, it turns out that the perimeter and area functions can be written in a special way to make them go pretty quickly. First, because we're dealing with a square, we know that all four side lengths are actually the same. So the perimeter is just 4 times 10.5, which of course is the same as 10.5 plus 10.5 plus 10.5 plus 10.5. But I like to think of 4 times 10.5 as a lot easier and a lot quicker than writing down 10.5 plus 10.5 plus 10.5 plus 10.5. So I'm going to calculate the perimeter of this square by just finding 4 times 10.5. And when I do, the answer is that the perimeter is 42 units once I complete that multiplication. Now, what about the area? Well, here's a place where perfect squares come into play. Why? Because the area of a square is base times height, and because the base equals the height, we know then that the area of the square is just the base squared, or the base raised to the second power. And that's really nice. So in this problem, the area of the square is 10.5 raised to the 2, or 10.5 squared if you want to use that language. And that's equal to 10.5 times 10.5. And if you calculate that product, that decimal number product, it's going to equal 110.25 square units once you're done with the calculations. Now, I'd like to move to another example that involves parallelograms. And in this case, it's not going to be a square and it's not going to be a rectangle. It's just going to be a parallelogram. Let's find the area of the parallelogram that is shown here. Now, I want you to notice that the base length here is 17. And it's important to see that the height here is not one of the legs of the parallelogram, but the height has been identified for us as 7 units. And just like with the triangles, the height might need to be measured some other way. It doesn't necessarily have to be one of the legs of the object that you're studying. Well, believe it or not, the area of this parallelogram is exactly the same as the area of a rectangle with base length 17 and height 7. You might not believe me at first when I say that, but let me try to convince you of this visually. I want you to start by focusing your attention on the triangle that is sort of sticking out on the left side of this parallelogram. Notice that that is a right triangle. Now, imagine that we take that triangle, cut it right off of the parallelogram, and move it over to the right-hand side of the parallelogram and sort of glue it back on. In doing so, don't distort that triangle, don't stretch it, don't try to do anything to mess up its basic shape and size. And if you think about it for just a moment, that triangle will then fit perfectly over on the right-hand side of this parallelogram, just as you now see on the screen. But now let me ask you, if I just ignore that height line for just a minute, what kind of object have I just constructed by doing this surgery, if you will, on the parallelogram? Well, in doing so, I've built a rectangle. And since I didn't distort the shape of the triangle as I moved it over from left to right, it turns out that the area of this rectangle must be the same as the area of the original parallelogram with which we started. And I think that's pretty cool. Now, since the base of this new rectangle is the same as the base of the parallelogram we started with, and the heights are also the same, it turns out that the area of the parallelogram must simply be base times height. So basically, we just wrote down a proof that the area of the parallelogram is base times height, just like it would be for a rectangle. Now, let's finish this problem with the specific numbers we started with. You probably forgot that we had an original problem here. We're supposed to be finding the area of a parallelogram with base length 17 and height 7. Well, then that area is just 17 times 7. It's base times height, and that is 119 square units once you multiply 17 times 7, and we're done. Now, time doesn't permit me to talk at length about other kinds of four-sided polygons, things like trapezoids, for example. But I would encourage you to look through a nice geometry textbook if you want to learn more about other kinds of quadrilaterals. Now, let me close by just commenting that we've talked today about triangles, we've talked about quadrilaterals or things that we like to call parallelograms or rectangles or squares. It's very important that you nail down this kind of information about triangles and these four-sided polygons as well. Next time, I want to continue this conversation about geometry by looking at polygons that have more than four legs. And I also want to look at one of the most important geometric shapes out there, and that's the circle. And I'll see you then.